In 9.5, we're going to go back to looking at angles in the XY plane instead of looking at arc length. So I don't know if you recall, the goal was to look at the unit circle with arc length and define our trig functions. And then from there, we would graph all of those trig functions in the XY coordinate system. And then the next step is to, instead of talking about arc length, talk about an angle theta, and then move from the unit circle to any radius, which is what we're going to do in 9.5. Now, if you look at this diagram here, we have some angle theta that is in quadrant 2 in this example, and this angle corresponds to a ray with the initial side on the positive x-axis and the terminal side in quadrant 2. So it's in standard position. And notice that there is a point on this ray. The distance here from the origin to that point is our distance r for a radius. So it's going to be some positive distance. Now, if we look at that point and we draw ourselves a vertical line from that point down to our x-axis, what we've done here is we've created a right triangle. So this right triangle is going to have a hypotenuse of r. One side is going to be an x value and the other side is going to be a y value. And this is where we're going to start creating these right triangles. We're going to take them out of the xy plane and let them stand alone on their own. But first, let's go ahead and review our Pythagorean formula that says in any right triangle, if you take and square the two smaller sides, so a squared plus b squared, you'll get the square of the longest side, which is our hypotenuse. In this case, this would be r. And our triangles have sides x and y. So we would have x squared plus y squared is equal to r squared. Now I'm going to go ahead and just rewrite this because I want to solve this for r. At this point, I would square root both sides. Normally, we would add a plus minus, but since this distance from the origin out to the point, that r distance is always going to be positive, I can just write the square root of x squared plus y squared. So what we're doing here is we're getting ready to talk about, I don't know if you remember SOHCAHTOA. So sine is if you have an angle. So let's look at this red triangle that I drew. If we look at this angle here, and I'll call this something else, I'll call it alpha. If I was looking at sine of, in this case, I wrote alpha, it's going to be the opposite side from the angle. So that would be that y value over the hypotenuse. In this case, this is an r value. And with respect to that angle alpha, if I was looking at cosine, it would be the sine adjacent, which is the x over the hypotenuse, which in this case is r. And tangent of this angle alpha, if we look at tangent with respect to alpha, it's going to be the opposite side over the adjacent side to the angle, so y over x. So that's where we're going with this. We're eventually going to get to that sine is the opposite over the hypotenuse, so cosine is the adjacent side over the hypotenuse, so ca. And tangent is opposite over adjacent side to the angle, so SOHCAHTOA. Now we're going to go back to our trig functions, and now we're going to write them in terms of an angle theta instead of arc length. So in this definition, we have given any point. And this is any point in our coordinate system. Let's go back up. Pick any point, some random point. Maybe not a big point like that. So pick any random point. It doesn't matter. We can always write some angle that corresponds to that point, starting on the positive x-axis, terminal side going through that point. So any point in our xy coordinate system, we can find an angle and go out some radius r to that point. Where given that angle theta, our r value is going to be equal to the square root of x squared plus y squared. So when we look at our trig functions now in terms of this value r, which again, we're moving away from the unit circle, so r doesn't have to be 1. It could be any positive number at all. We have our sine. Oh, interesting. Our theta got reformatted when I saved it. So sine of, this is supposed to be a theta, is equal to y over r. So opposite over hypotenuse is r. Cosine is x over r. Tangent is y over x. And then we have the reciprocal functions. If sine is y over r, then cosecant, which is its reciprocal, is r over y. Secant is r over x because it's the reciprocal of cosine. Cotangent is reciprocal of tangent, so that would be x over y. So it's similar to what we've been talking about all along, except for we're just using different variables. In example 1, we have the terminal side of some angle theta. It's in standard position, so initial side on the positive x, and then we go around and we have some terminal side. Vertex is on the origin. So in standard position, and it's passing through this point 4, -3. That would be our x value is 4, and our y value is -3. We want to find all the values of the 6 trig functions. Now, I can find the tangent and the cotangent right away because they're only written in terms of x and y. So right away I get the, okay, this is going to bother me. Oh, it's not going to go away. Right away I get the tangent of theta is y over x, so -3 over 4. And I get cotangent of theta is, flip it, so -4 over 3. I can't get any of the other 4 without knowing what r is. So first I have to solve for r. And that's going to be the x value squared, so that's 16, plus the y value squared, so we're squaring -3 times -3, it's going to turn to a +9. And then we would have the square root of 25. So this turned out to be nice, turned out to be 5. But you know, you could end up with an r with a square root, like square root of 2, and in that case you may have to do some rationalizing of denominators. So we have tangent, we have cotangent, I can get sine. So sine is going to be the y, which is -3, over the r, which is 5. I can get cosine. Cosine is going to be x over r, so 4 over 5. And once I have sine, I have its reciprocal cosecant. All I have to do here is flip to get -5 over 3. And then, oops, meant to write secant. Flip cosine, you get 5 over 4. So let's just double check. This point 4, -3, if I do a little sketch, 1, 2, 3, 4, 1, 2, 3, we're in quadrant 4. So in quadrant 4, all the trig functions are negative except for cosine and secant. And I could see here that cosine is positive, secant is positive, and all the rest of these trig functions are negative. So that's just like my double check. And you always want to be conscious of which quadrant you're working in, because you are going to need to choose oftentimes whether you're going to make your values negative or positive. So let's go to our identities. And again, these are all the identities we had before pretty much, but now we're just, instead of using arc length, we're using our angle theta. Pythagorean identity, sine squared plus cosine squared is equal to 1. And then we get 1 plus tangent squared is secant squared, 1 plus cotangent squared is cosecant squared. We have our reciprocal identity. So remember, sine is equal to 1 over cosecant, but cosecant is 1 over sine because they're reciprocals of each other. So if cosine is equal to 1 over secant, then secant must be equal to 1 over cosine, again, reciprocals of each other. And then we have tangent, 1 over cotangent. Cotangent is 1 over tangent, reciprocals of each other. We also have this new way of just writing reciprocals, and that would be what we call the quotient identities. So if you look at the tangent, it's y over x, but sine is y, cosine is x. So another way that you could write tangent is sine over cosine. And then if you flip it, you get cotangent, which is cosine over sine. Now in example 2, we're going to use an appropriate identity to find each function value. And I have sort of a trick in here. So we want to find sine of theta, given that cosecant of theta is equal to 5 over 7. So if you're on autopilot, you think, okay, sine, cosecant, they are reciprocals of each other. So if I know that cosecant is a positive 5 over 7, that must mean that sine of theta is equal to 7 over 5. And I put this in as a trick question. It's actually not true. Now remember when we went over the graph of sine and the domain and range of sine? The values of sine are always between -1 and +1. It can be equal to -1 and it can be equal to +1, but it's everything in between. It cannot be smaller than -1 or larger than 1. So to get sine of theta equal to 7 over 5, that can't happen. But also look at cosecant. When we looked at the range of cosecant, remember we took away -1 to 1? So cosecant is equal to 1 to positive infinity, or we could take -1 to negative infinity, or -1 to negative infinity, yeah. So it's impossible for cosecant, for given any angle theta, to be equal to 5 over 7. So in this case, this is undefined. Now your book is really nice. It's going to give you all these defined things when we're dealing with this type of problem. But just be aware that we do have domains and ranges for all of these trig functions, and we have to stay within that. In example B, we want to find the cotangent of theta, and we're given that tangent of theta is equal to negative square root of 2 over 3. So first of all, I'm trying to find cotangent, and I have tangent. Well, I do know that they're reciprocals of each other, so if I have tangent, I do have cotangent. So all I have to do is write cotangent of theta is equal to -3 over the square root of 2. But then again, got to rationalize denominator by multiplying top and bottom by the square root of 2. So the cotangent of theta is going to be equal to -3 times the square root of 2 over 2. And that's a good value. What's really nice about working with tangent and cotangent is their domain is restricted because they have these vertical asymptotes, but their range, what they give back, their so cotangent of theta equal to -3 over square root of 2 over 2, it doesn't matter because of the graph. Remember, it went from negative to positive infinity, the y values. So you can get anything back from cotangent and tangent. We don't have to worry about that. In example 6, we want to find all 6 trig functions. I don't have to find secant because I'm given that secant is equal to -4. Secant of theta is equal to -4. Okay, so that is a good value because remember, secant is a reciprocal of cosine. It cannot take on values between -1 and 1, but smaller than -1, like -4, yes, it can work, and then greater than 1. So this is a good value. I also know that tangent of theta is greater than 0, so tangent is positive. And what's going to help me when I find all of the trig functions is that to know that secant is negative, tangent is positive. So first of all, tangent is positive in quadrant 1 and quadrant 3. Secant has the same sign as cosine does, and cosine is negative in quadrants 2 and quadrant 3. So this must be quadrant 3. And that may be important to us when we start finding the other trig functions. So I do have secant, which means I have its reciprocal, which is cosine. Cosine of theta is going to be flip it, so it's going to be -1/4, good value. And if secant is negative, cosine's negative, especially if you're in quadrant 3, cosine's negative. And now I'm stuck. So I'm going to go back to my identities. I do have cosine, so I could find sine by using sine squared of theta plus cosine squared. So that's going to be -1/4 squared equal to 1. And then solving here, we have 1 minus, so this is going to be 1/16. It looks like sine squared is equal to 15/16. So I need sine, not sine squared. Now, normally I would put a plus and minus and the square root of 15/16. But we're in quadrant 3, so I know in quadrant 3 sine is negative, which means my sine of theta is going to be the negative choice. And simplifying, I have the square root of 15/4. So we have sine. Secant was given. We have cosine. And once we have sine, we have cosecant. Because cosecant of theta is the reciprocal of sine, so it's going to be -4 over the square root of 15. And then we have to rationalize, which means cosecant of theta is going to be -4 square root of 15 over 15. Look at 4 of them. It looks like I'm missing tangent and cotangent. Going back to those quotient properties, I know that tangent of theta is equal to sine over cosine, and sine is negative square root of 15/4. Cosine is -1/4. Now I'm in quadrant 3, so I know the tangent has to be positive, and I could see that it is because the negative over negative will cancel. And also remember that when your denominators are the same, you can cancel those as well instead of going through all the changing it to multiplication, keeping the top fraction, flipping the bottom, and so on. So this is going to be square root of 15, and it's a positive square root of 15. The last thing I need is cotangent, but I have tangent, so it's reciprocal cotangent. It's going to be flip 1 over the square root of 15. And again, we have to rationalize. So multiply top and bottom by square root of 15 over square root of 15. And I have cotangent of theta is equal to the square root of 15 over 15. All right. We got them all. And the last thing we're going to talk about here is something that's going to come up later. We have these identities, like we have the Pythagorean identity, we have the reciprocal identities, and we have these quotient identities. And we're going to keep adding on and finding more and more identities. Well, eventually we're going to have to write proofs where we have to prove some of these identities. And that's not solving an equation. It's very abstract, and sometimes it's hard for people to grasp. So this is sort of an intro into this abstract idea of writing proofs. So in example 4, it says use identities to write cosine in terms of tangent. So what that means is we want to take cosine and write it equal to something that has tangent in it, but no other trig functions, just tangent. Now we're allowed to use numbers and square roots and all that stuff, but only tangent. And we know that theta here is in quadrant 2. So since we're in quadrant 2 and we're trying to write cosine equal to something with tangent, in quadrant 2, I know that it's going to be negative because cosine is negative in quadrant 2. And there's a variety of ways you can approach this. First of all, if you looked at your identities, if you saw an identity where there was cosine and tangent together and nothing else, then that would be a good choice. We do have that quotient identity where we have sine of theta over cosine of theta equal to tangent. So I could play around with that and change that to cosine equal to sine over tangent. Let's see, if I multiply both sides by cosine, divide by tangent, I could change this around, but there's a problem here. I have that sign there that I need to get rid of. So I don't want to do that. That's too many steps for me. But you can do it this way. Instead, what I'm going to look at is I'm going to look at cosine of theta equaling to 1 over secant of theta. That's simpler for me to use. And then I also know that going back to the Pythagorean identities, I know that secant squared theta is equal to 1 plus tangent squared theta. So what I could do is like a two-step process. I could take this second equation and I could solve that for secant, and then I could just replace the secant. Because if I solve this for secant, on the right-hand side, I'm just going to get an expression that only has tangent in it. Okay, so let's do that. I'll get secant of theta is equal to plus or minus, because I'm square rooting both sides, 1 plus tangent squared theta. Again, this is not the only way that you could do this. And remember, cosine has to be negative. So I've already got 1 in the numerator. That means the secant that I choose has to be the negative one. So I would write cosine of theta is equal to 1 over negative square root of 1 plus tangent squared theta. And I have done it. I have written cosine in terms of tangent, no other trig functions. So again, a little bit abstract. You always have to kind of play around with the identities and keep in mind whether your final answer is going to be negative or positive. So that is it for this section.